Okay, in the interest of time, we'll blast through this. So the moment of inertia is the integral of r squared dm. In this case, I'm using the symbol x for the distance away from the rotation axis. So this will be the integral of x squared. And the little bit of mass at distance x away can be represented as the mass per unit length times a little bit of length. And the mass per unit length is just all the mass over all the length if it's uniform. So I have m over d dx from 0 to d. So that is m over d x cubed over 3 evaluated between 0 and d. That is to say 1/3 md squared. Okay, now I gotta blast through the parallel axis theorem. Okay, so suppose that I compare the inertia of a weight when it's near the axis to when it's farther away. We know that the moment of inertia is the sum but is there a way to leverage, if we know the moment of inertia for rotation about some axis, is there a way to simplify a calculation if it rotates about a different axis? So suppose that I knew the moment of inertia of something when it was rotating about an axis of symmetry or axis passing through the center of mass. And I now translate the axis to the side. So what would I get? So I is the sum of mi ri plus, and I'm going to displace by big R, okay? So I'm just going to move the axis away by a distance capital R. Okay, I can evaluate this using the dot product, sum on I, m sub I, ri vector plus capital R vector dotted into ri plus capital R. That should give me 4 terms. But 2 of them are going to be the same and also drop. So I have ri squared. I have plus 2 ri dot r. And I have plus r squared. Can someone make the argument for why, if we say that the original calculation is done passing through the center of mass, then I can drop this term. So remember, the center of mass satisfies the sum on I, m sub I, r sub I is 0. The first moment is 0. So that means since big R vector is a constant, I could pull that out of the sum, and I'm left with m sub I, r sub I vector. But if I measure from the center of mass, that disappears. And I'm left with the moment of inertia is equal to the sum on I, m sub I, r sub I squared, where this is with respect to the center of mass, plus what's left is the sum over all the masses, that's the total mass, times r squared, the distance that I've moved the center, the axis of rotation away from the center of mass. So we're out of time. I would let you confirm that you could use this in reverse to determine that the moment of inertia for the rod rotating about its center will be 1/12 md squared.